Hi guys, Mrs. Brumwell here. We're moving on to section 2.2. We're going to talk about something called differentiability, and we're going to kind of connect it to what we know about continuity. Okay, so we have talked about what the derivative is, and we have used this definition. This limit is our derivative of a function at a given number. Now, we can also define a derivative as another function, and we call this the derivative function. Now, this should look familiar to you guys. This is the difference quotient. So the limit as h approaches 0 of the difference quotient is the derivative function. So this is what I use if I want to find the derivative of at a particular point. This is what I want to do if I just want the derivative function. Okay, so we're going to kind of practice the second one. You guys did a lot of this first one in 2.1. We're going to practice finding the derivative function. Okay, so if, and then kind of tying it back to that word differentiable. So if f has a derivative, if we find the limit exists, then we say that it's differentiable. If we find the limit does not exist, then we would say it's not differentiable. Okay, so we're going to find the derivative function of this f of x. So we're going to use the second definition. So we're going to find the limit as h approaches 0 of f of x plus h. So reminder, f of x plus h is taking x plus h and replacing every single x with x plus h. So for this particular function, that's going to be x plus h squared minus 5 times x plus h. Now remember, this expands into x squared plus 2xh plus h squared, and then distributing that negative 5. So that is what f of x plus h equals. So I'm going to put that here. So we've got x squared plus 2xh plus h squared minus 5x minus 5h. Okay, so that's f of x plus h. Now minus f of x. So here's f of x all over h. So my goal is to be able to divide h out, because I right now have division by 0 if I were to substitute in 0 for h. So I'm going to simplify, combine some like terms, and then hopefully be able to divide out my h. So I get x squared and negative x squared. Negative times negative 5x makes that positive 5x, which will cancel with that negative 5x. So we're down to the limit as h approaches 0 of 2xh plus h squared minus 5h over h. So another way I could write that is I could factor out this h from the numerator and say we have 2x plus h minus 5. And now I can divide out that h. So now I get the limit as h approaches 0 of 2x plus h minus 5. So now if I substitute in 0, we're good. We don't have division by 0. So if I plug in 0 for h, I'm left with 2x minus 5. So this is my derivative function. So it's a function because it's still in terms of x. So it's not just a number anymore. So we're going to say f prime of x equals 2x minus 5. So notice again, there's no number right now in here for x. We're just saying the derivative function is 2x minus 5. Something kind of helpful just to recognize to you guys, whatever function I start with, if it's a polynomial function, my derivative function is always going to be 1 degree less. So if I have a squared function, I should get something to the first power as its derivative. We're going to talk more about that in the next section. Okay, this next one says differentiate. That's another term for find the derivative function. Okay, so we're going to use the same exact thing. We're going to find the limit as h approaches 0 of, okay, x plus h in for x, right? F of x plus h minus f of x over h. Okay, again, if I were to substitute in 0, I have a problem, right? So with radicals, we want to multiply by the conjugate to see if we can get some things to cancel nicely. So I'm going to multiply this by x plus h plus square root of x. And we're going to do the same thing on the top and the bottom so that we're really just multiplying by 1. Okay, remember when I multiplied, this is kind of like difference of squares in factored form. So when I put it back together, it ends up being this squared. I might write that out so you guys can see that. So square root of x plus h squared minus square root of x squared, right? So if I'm putting difference of squares back together, that's what it's going to be. And then on the bottom I have h times x plus h squared of x. Okay, and then I dropped my limit notation, which I shouldn't yet, limit as h approaches 0. Okay, so if I square these, my radicals go away. So we're left with the limit as h approaches 0 of x plus h minus x over, and I'm just going to leave this denominator like this for right now. Okay, so nicely, x and negative x, right, cancel, and then h divided by h cancels. So we're left with the limit as h approaches 0 of 1 over this denominator, x plus h under the radical plus square root of x. Now if I plug in 0 for h, we get 1 over square root of x plus 0 is still square root of x plus square root of x. And then I could just write that as 1 over 2 root x. So that is my function. Again, I could write it as f prime of x is equal to 1 over 2 root x. Oh, no, I wrote 2 square roots there. Don't need that. All right. The surface area S, measured in square meters of a balloon expanding as a function of time t in seconds, is given by this equation. Write the rate of change. Remember, this is instantaneous rate of change is implied, and that means we're going to use that limit definition of a derivative. Okay, so of the surface area of the balloon with respect to time, what are our units of S prime of t? So they're asking us to find the derivative of this function. So we're going to use that same thing. So we're going to say S prime of t, so the derivative of S, and we're going to use our definition. So this time I'm doing t plus h instead of x plus h, but we're going to do 5 times t plus h squared minus 5t squared. So f of x plus h minus f of x, in this case s of t, okay, and then over h. Expand the top, right? Oh, and I forgot my limit. Sorry, you guys. Okay, so we've got s prime of t equals the limit of this function as h approaches 0. Okay, so expands, and we get, keep your limit notation. Okay, 5t squared plus 10th plus 5h squared. So that's expanding that and then multiplying everything by 5 minus 5t squared over h. Okay, so my positive 5t, negative 5t squared go away. We can divide out an h from both of those. So we get the limit as h approaches 0 of 10t plus 5h, right? If I divide an h out of both of those. Now plug in 0 for h, and we just get 10t. Okay, so this is my derivative. So s prime of t equals 10t. And then they're asking, what would the units be? Okay, so remember, this is a rate of change, how fast something is happening. So it's talking about a balloon expanding. So it's talking about the surface area of a balloon with respect to time. So the surface area is in square meters. So we would say square meters or meters squared per second. Okay, so that's a rate. We're comparing like a distance or unit of measurement over a unit of time. So that would be the proper units to go with this. All right. Okay, next we are going to use the graph of f of x to help us graph f prime of x, the derivative function. Okay, so something to remember is the slope of each tangent line is going to be actually the y coordinate on the derivative function. Okay, so here's f of x. This is f of x. So we can see the slope here, they approximated the slope to be about 12. So then at -2, they put a point at 12. So this y-coordinate matches this slope, okay? At this one, they said a slope of about 3. So at -1, they have a slope of 3. So those, again, match. Okay, the slope they approximate here to be 12, etc. So we're going to do an example just like this. Okay, so we're going to use, here's my f of x graph. We're going to try and estimate the graph of the derivative, f prime of x. Okay, and we're just going to do it on the same graph, but let's kind of estimate some things. So the biggest thing I like to find is these horizontal lines, because what is the slope of any horizontal line? Well, my slope there is 0, right? Horizontal line. Okay, so I have another one of those right here. So those are easy to identify. The slope is 0. Another nice one, right? Kind of 45 degrees through the origin. I would probably estimate my slope there to be -1, okay? If it was going this way, I'd estimate +1. So at this value, I'm going to say that my slope is -1. Okay, so this one's a little steeper than this guy, and it's going in the positive direction. You can kind of use like count, rise over run. You can kind of estimate that, you guys. I estimated this slope to be about 4. Okay. And then this one over here is even steeper, and it's in the positive direction. So I estimated this one to be about 6. Okay, so now I kind of have 6 new points, okay? So I'm going to use the same x value, but now I'm going to use the slope as the y value to go with it. So my new point is going to be at -4, 6. So -4, there's 4. We'll go up a little higher for 6. So this point's going to be at -4, 6. So this is on the graph of the derivative. Okay, so here's f of x. This one's going to be f prime of x. Okay, the next one I have is -2, 0. So this point is going to be at -2, 0. Okay. Okay, this one we estimated to have a slope of -1. So 0, -1. Okay. And then this one has a slope of 0. So keep the same x value. This is my new y value. So 3/2, 0. And then we said our slope's about 4 here, so 3, 4. This one's going to go like right over f of x, sorry. Okay, and then I'm just going to connect kind of with a smooth curve. It's kind of looking like a quadratic-ish. Or maybe a 4th degree, some even polynomial. All right, so this one is f prime of x. So again, the slope at those different points becomes the y coordinate of the derivative function. Okay, next. Sorry, I got too many papers here. Okay, all right. Now we're still going to talk about the graph here, but we're going to tie it back to what we know about limits and defining a derivative. Okay. So we're going to say there are places where I can have a function that's continuous, but not differentiable. So the limit of our definition of derivative, f of x minus f of c over x minus c, does not exist. So this is like an absolute value graph. So it's continuous, right? It's defined everywhere. There's no gaps, holes, asymptotes, nothing like that. So it's defined everywhere. It's continuous. But it has this sharp corner. And so when that happens, the derivative does not exist. So the left and right limits are existing, but they're not equal for the derivative, okay? So this one is not differentiable, okay? This is another example of a continuous function that's not differentiable at 0. In that case, this one also 0, because I have a vertical tangent line. So we know vertical lines have undefined slope, and the slope of that tangent line is our derivative. So if the slope's undefined, so is the derivative. So the derivative does not exist there at 0. And then we have this thing called a cusp. It's very similar to a corner, but it kind of deals more with a curve coming in and meeting at a point kind of harshly like this. We call that a cusp. And that, again, has a vertical tangent line. So the slope of the tangent line right there is going to be undefined as well. So the derivative is undefined at 0. Okay, so those are kind of 3 different things we can see. 3 ways that this can happen. We can have a corner, we can have a vertical tangent line, or we can have a cusp. Okay, and these are some kind of specifics as to what happens with the limits to tell us that. So we're going to kind of use that down here on these 2 examples. So we have these 2 graphs, and we're asked to determine, do they have any horizontal tangent lines? If yes, explain and identify where they occur. All right, so where these occur, we have, I'm going to put A down here, so we're answering A. Okay, so does the graph have any horizontal lines? So this is kind of doing the opposite of what we just did. So we took the graph of f of x and then graphed f prime. Now we're given f prime. So this is the derivative. So we're trying to go backwards. What did the original function look like? So if there are zeros, that's where the horizontal line was tangent. Okay, so we're going to say yes. So we're looking for zeros. So this would be 1 and this would be 1. So we would say at x equals -4 and x equals 0. Okay, and why? Because remember the y coordinate, so here's kind of my reason. The y coordinate of 0, so we have, right, y is 0, y is 0. So a y coordinate of 0 indicates the slope of the tangent line of f of x is 0. Okay, so that anytime I have a slope of 0, right, we know that's a horizontal tangent line. Okay, so we do have 2 places where I have a horizontal tangent line on f of x. Does the graph have any vertical tangent lines? So if I go up here, vertical tangent line, the one-sided limits both equal positive infinity or negative infinity. Or both one-sided limits are infinite, but equal infinity and the other equals negative infinity. So if we look at this graph, okay, and we look kind of for those infinite limits. So do we see the graph shooting to positive infinity or negative infinity? And we do right here, right? So the left-sided limit is going to positive infinity, and the right-sided limit is going to negative infinity. So we do have a vertical tangent line at x equals -2. Okay, and this is going to be a cusp. Okay, and here's why. Both one side are infinite, but one goes to positive infinity and one goes to negative infinity. So we could say something like left limit goes to positive infinity, right goes to negative infinity. Okay, so left goes to positive, right goes to negative. So if I have one positive, one negative, that always tells me there's a cusp. All right, last one, C. Does the graph have any corners? So here's how I see if the corner. The limit, the left-hand limit exists, the right-hand limit exists, but they're not equal to each other. Okay, so that happens when I have a jump like this with a hole. So my left-hand limit of this one would be 1. My right-hand limit would be 4. Those are not equal. So this is a scenario where we have a corner at x equals 2. Okay, and this would be because right and left limits exist, but are not equal. Okay, we're gonna do the same thing for 6. I'm not gonna write out the explanations here, you guys. We're just gonna identify where these happen. Okay, so horizontal tangent line. So I'm looking for zeros. So we got a 0 at -2, not here because it's not included. So -2, 1, and 2. So yes, at x equals -2, 1, and 2. Okay, vertical tangent line. So we're looking for basically vertical asymptotes. Anytime my graph's going to infinity or positive infinity, so we have one right here at -1. So if they're both going the same direction, it's not a cusp. So I'm just going to put that here, not a cusp. The cusp only happens if I have one going positive, one going negative. All right, and the last one, do we have any corners? Remember, that happens when I have the jump. Left hand and right hand both exist, but they're not approaching the same value. So yes, and that's happening at x equals 0 right here. All right. Okay, last part, you guys. All right. We, again, are now going to try and connect continuity and differentiability. So if a function is differentiable at a number, c, then f is continuous at c. So if we can find the derivative and it exists, that also indicates that the function is continuous at that number. So if a function's not continuous, then it's not differentiable, okay? So basically, if we can differentiate, that implies continuity. But continuity does not imply differentiability. And that's because we just saw 3 examples of continuous functions that had points that were not differentiable. The corner, the cusp, or the vertical tangent line, okay? All right, so we're gonna determine whether the function is differentiable at c, and then we're gonna find the derivative if it has it. Okay, so let's start with A. So the first thing we should do is we should verify continuity, because if it's not continuous, then it's not differentiable. Okay, so we're first going to look at it's continuous. So if I look at the left and right limits, and for C is 0 for A, if I plug in 0 for both of those, I get 0, and f of 0 is also 0. So this is continuous. Okay, so that's kind of first. We want to verify continuity first. Okay, now we're going to look at the limit. So we're going to use our limit, our derivative definition at a function. So as a reminder, sorry, I put that somewhere. Here we go. Okay, so we're going to use this, right? The limit at a number. Okay, because it's a piecewise function, we are going to do left and right limits. So we're going to do the limit as x approaches 0 from the left. Okay, so I'm going to use the left here. So we've got f of x is x cubed minus f of 0 over x minus 0. Okay, so if I simplify, we get x cubed over x, which is x squared. So we get the limit as x approaches 0 from the left of x squared. So now if I substitute in 0, I just get 0. Okay, so we're going to check the right-hand limit. So now we have the limit as x approaches 0 from the right. Okay, so a piecewise function, that's going to be this bottom one. So we're going to use our derivative definition. So we've got f of x minus f of c over x minus c. Okay, and again, if I simplify this, I end up with x squared over x, which is just x. And if I plug in 0, I just get 0. So because those agree, right, this means f prime of 0 is 0. Okay, so we got the same limit for the left and the right. So we have it being differentiable. So we're going to say f of x is differentiable at 0, and then we can write the derivative is 0. When we found the limits, they were both 0. Okay, for this other one, B, we're going to do the same exact thing. Look at continuity first. So if I were to find the left-hand limit, plug in 1. 1 minus 2 times 1 is negative 1. 1 minus 2 is also negative 1. We get the same thing for f of c, so this one is continuous. Okay. All right, now we're going to find the left and right-hand limits. My c value is 1 in this case, so we're doing as x approaches 1 from the left. So f of x minus f of c over x minus c. Okay, so here I get 1 minus 2 is negative 1. Minus negative 1 is going to be plus 1. So after simplifying the top there, we get negative 2x plus 2 over x minus 1. We can factor out a negative 2 from the top. Oh, sorry, I changed that to a plus sign, sorry. Still finding from the left. Okay, so if I factor out a negative 2, then I can divide out my x minus 1s, right? So we would get the limit is just negative 2. Okay, so we got the left hand to exist. Now let's find the right hand limit. So as x approaches 1 from the right, so now we're going to use this piece, greater than 1. So f of x is x minus 2 minus f of c. So now we're plugging in 1 for x. And then over x minus c. So let's see, we get negative 1 plus 1, negative 2 plus 1 is x minus 1. Okay, so then we get the limit as x approaches 1 from the right of x minus 1 over x minus 1. Divide that, and I just get 1, right? Okay, so we got both limits to exist, but they're not equal to each other. Okay, so because anytime we get the one-sided limits not to agree, the limit does not exist. So we would say f prime of 1 does not exist. And remember, if we get those one-sided limits to exist but not agree, that just tells us that f of x has a corner. at x equals 1. Okay, so does not exist because our limits don't agree left and right, and that's because there's a corner on our graph of f of x. All right, guys, that's it for this video. Thanks for watching.